more than 700 meters beneath the Atlantic, where sunlight has never reached and pressure can crush ordinary machines. Something has been quietly growing for longer than human civilization has existed, something that shouldn't exist according to everything scientists believed about hydrothermal systems. It doesn't glow with molten lava or erupt with violent explosions. Instead, pale towers rise from the darkness as though an abandoned stone city had somehow appeared on the ocean floor. When scientists first saw the images, their instruments weren't the only things they questioned. They began questioning decades of geological understanding. The expedition had not been searching for a biological wonder. Their mission was far more ordinary: map fractures in an underwater mountain range and better understand how Earth's crust slowly reshapes itself. Every expectation pointed toward familiar volcanic vents, but the cameras revealed something entirely different: structures that looked ancient, almost architectural, standing far from where conventional hydrothermal systems were ever expected to exist. The deeper the team investigated, the stranger the contradictions became. The surrounding rocks suggested old, inactive seafloor. The vent fluids were unexpectedly cool. Even the minerals forming the towers were unlike those found in the famous black smokers that had transformed marine biology only decades earlier. Nothing matched the scientific model that had guided deep-sea exploration for decades. If the discovery had simply been another unusual vent field, the mystery would have ended there. Instead, every new observation dismantled another assumption. If magma wasn't driving this hidden landscape, then what invisible process had spent thousands of years constructing an underwater city where life seemed least likely to survive? The discovery posed a simple question that refused to go away. If these towering chimneys weren't powered by magma, then what had been building them for thousands of years? To answer it, scientists had to look beneath the city itself. The Lost City sits along the mid-Atlantic ridge, where Earth's crust is slowly pulling apart. Most hydrothermal vents form here because molten rock heats seawater trapped underground, forcing superheated, mineral-rich fluids back through the seafloor. It was a well-tested explanation, except it couldn't account for what researchers were seeing. The White Towers stood far from the ridge's volcanic center, above ancient mantle rock instead of an active magma chamber. At first, that seemed impossible. Then the rocks revealed a different story. Seawater had been slipping through deep fractures for countless years, reacting with minerals such as olivine in a chemical process scientists call serpentinization. As the rocks transformed, they released heat along with hydrogen and methane, energy-rich gases created without volcanic fire. One mystery had finally been explained, but the answer was even more astonishing than the question. Here was a natural system generating its own source of chemical energy, largely independent of both sunlight and magma. The White Towers were not the product of an underground furnace. They were the visible expression of an invisible reaction that had been quietly reshaping both rock and water for millennia. If ordinary rock and seawater could create the energy needed to sustain an entire ecosystem, then another assumption suddenly became much harder to defend. Perhaps life had never depended on the conditions scientists once believed were essential. The next question was no longer how the towers formed, but what exactly was living on them. Once researchers understood what powered the Lost City's vents, attention shifted to an even greater mystery. The towering chimneys had captured everyone's imagination, but they were only the setting. The real discovery wasn't the city itself, it was the civilization quietly thriving across its pale mineral walls. Almost every complex ecosystem on Earth ultimately depends on sunlight. Forests, oceans, and even the air we breathe trace their energy back to the sun. The Lost City breaks that rule completely. For a moment, that forces an unsettling question. How many environments have we dismissed as lifeless simply because they didn't resemble our own? Instead of relying on photosynthesis, Dense communities of archaea and specialized bacteria survive by harvesting energy directly from hydrogen and methane released through the ongoing reactions between seawater and mantle rock. At first, that seemed to explain everything, but it immediately raised another mystery. If microscopic life could flourish here, what kind of ecosystem had formed around it? The answer emerged as scientists examined the towers more closely. Thin microbial films coated the chimneys like living skin, providing the foundation for an entire food web. Small shrimp, snails, crustaceans, and other hardy organisms depended on these microbes, creating a thriving ecosystem powered not by sunlight or volcanic heat, but by chemistry occurring deep beneath the seafloor. The implications stretched far beyond marine biology. The Lost City was no longer just a geological anomaly. It had become compelling evidence that life can flourish wherever a dependable source of energy exists, even in places once dismissed as completely uninhabitable. If that idea held true here on Earth, perhaps scientists had been looking for living worlds in the wrong places all along. The implications didn't stop at the bottom of the Atlantic. As researchers pieced together how the Lost City functioned, an unexpected realization began drawing the attention of an entirely different scientific community. This strange ecosystem wasn't just changing marine geology, it was quietly reshaping the search for life beyond Earth. For decades, scientists assumed that worlds capable of supporting life would need conditions broadly similar to our own: liquid water, moderate temperatures, and above all, sunlight. The Lost City challenged that assumption. Here was an ecosystem proving that sunlight might not be the requirement everyone had imagined. Instead, life appeared to depend on something even more fundamental: a continuous source of usable energy. The search suddenly widened. Beneath the frozen crusts of Europa and Enceladus lie vast oceans resting against rocky interiors. Space missions have detected water, hydrogen, methane, and complex organic molecules escaping from these hidden seas. The ingredients sounded surprisingly familiar. For a moment, the comparison is difficult to ignore. If an ecosystem like the Lost City can survive in complete darkness beneath Earth's oceans, could similar chemistry be unfolding beneath kilometers of alien ice? But similarity is not proof. No spacecraft has discovered life beneath those distant oceans. What the Lost City offers is something arguably more valuable: a working example that chemistry alone can sustain an ecosystem for extraordinary lengths of time. It transformed one of Earth's strangest environments into a natural laboratory for astrobiology. Yet one mystery refused to disappear. If nature could build a place like this once, why hadn't scientists found another? After decades of exploration across the world's oceans, the Lost City still stood almost entirely alone, and that unanswered question would drive the next chapter of its remarkable story. The search for another Lost City did not stop with its discovery. Research vessels returned equipped with increasingly sophisticated sonar, autonomous underwater vehicles, robotic submersibles, and deep drilling systems capable of reaching farther into the oceanic crust than ever before. Scientists mapped vast stretches of seafloor, analyzed vent fluids, and searched for the same extraordinary combination of geology and chemistry. They uncovered remarkable hydrothermal systems, but every new discovery carried the same conclusion: something was always missing. Gradually, another pattern became impossible to ignore. The Lost City appears to exist because countless conditions aligned with extraordinary precision. Ancient mantle rock had to remain exposed. Seawater needed to circulate through deep fractures for tens of thousands of years. The chemical reactions had to continue with remarkable stability, uninterrupted by the violent volcanic activity that dominates most hydrothermal regions. Change any one of those conditions, and the entire system evolves into something completely different. Its rarity has made the Lost City more than a geological curiosity. It has become a scientific archive, preserving clues about the earliest chapters of our planet and offering one of the best natural laboratories for understanding how life might emerge elsewhere in the universe. Yet while scientists continue studying this hidden world, another reality has begun to surface. Growing interest in deep-sea mineral resources is bringing commercial attention to regions once considered beyond human reach. Researchers warn that disturbing ecosystems like the Lost City could erase evidence that has been quietly accumulating for over 100,000 years, long before humans ever wondered where life began. Pause for a moment and consider what that really means. This isn't simply an extraordinary place hidden beneath the Atlantic. It is a record of processes that may have shaped the earliest chapters of life itself, one that cannot simply be rebuilt if it is lost. Perhaps that is the discovery that matters most. The Lost City never simply answered a scientific question. It revealed how much remains unknown. Hidden beneath crushing darkness, where rocks slowly transform water into energy and life endures against every expectation, it reminds us that Earth's greatest mysteries are not always waiting in distant galaxies. Some have been here all along, patiently reshaping our understanding of what a living world can truly be.